Hi, welcome to my channel. This is Pushpita here. Dear class 12 children, the upcoming board exam have a great significance in your future. So this is the most crucial time to ready for the challenge. Let's start with the first chapter, relations and functions. In class 11, you have learned about the relation and function, domain, codomain, range, some specific real valued functions and their graphs. In this chapter, let us study the types of relations and functions, composition of functions and the invertible functions. Let us study the types of relations. First one, empty relation or void relation. A relation R in a set is called void or empty relation if no element of A is related to any element of A. That is, phi is a subset of A cross A. For example, a relation in a set A is equal to 1, 2, 3, 4 is given by R is equal to AB such that A minus B is equal to 10. It is an empty relation because there is no pair which satisfies the given condition. Next, universal relation. A relation R in set A is called a universal relation if each element of A is related to every element of A. That is, R is equal to A cross A. For example, a relation in a set A is equal to 1, 2, 3, 4 is given by R is equal to AB such that modulus of A minus B greater than or equal to 0. In the given example, you can see that each pair gives the difference positive, which is greater than or equal to 0. See, both the empty relation and universal relation are sometimes called trivial relations. Then, reflexive relation. A relation R in a set A is called a reflexive if A belongs to R for every A belongs to A. For example, a relation R in a set 1, 2, 3 is given by R is equal to 1, 1, 2, 2, 3, 3, 1, 2, 2, 3. In the given relation 1, 1, 2, 2, 3, 3 lie in R, that is reflexive. Remember that the universal relation on a non-void set is reflexive. See the next example. Let L be the set of all lines in a plane. Then relation R on L defined by L on L2 belongs to R, which is equivalent to L1 is parallel to L2. As you know that every line is a parallel to itself, the given condition is true. Therefore, R is reflexive. Symmetric relation. If AB belongs to R implies that BA belongs to R for all AB belongs to A. For example, let A is equal to 1, 2, 3, 4 and R is a relation on A is given by R is equal to 1, 3, 1, 4, 3, 1, 2, 2, 4, 1. In the given relation, both 1, 3 and 3, 1 belongs to R. Also, both 1, 4 and 4, 1 belongs to R. That is, if AB element R, there is BA element R. Therefore, R is symmetric. Remember that the identity and universal relation on a non-void set are symmetric. Transitive relation. If AB element R and BC element R implies that AC element R for A, B, C belongs to A. For example, 1. In the set of natural numbers, if the relation R is defined by x less than y is transitive. That is, if 3 less than 5 and 5 less than 7, then 3 will be less than 7, which is transitive. Second example, let A is equal to Z 1, 2, 3 and relation R is given by R is equal to 1, 1, 1, 2, 2, 1, 2, 2. See the relation. 1, 1 belongs to R, 1, 2 belongs to R. This implies 1, 2 belongs to R. That is, AB element R, BC element R implies to AC element R. According to the property of set, there is no element will be repeated. So, in the given relation, BC and AC represented the same ordered pair 1, 2. Equivalence relation. A relation R in a set A is said to be equivalence relation if R is reflexive, symmetric and transitive. Let's do some questions. Question 1. If R is equal to A cube such that A is a prime number less than 5, be a relation, find the range of R. See the question. As per the condition given, A must be less than 5 and also it must be a prime number. We know that 2 and 3 are prime numbers less than 5. Therefore, A can take the values 2 and 3. Then we get R is equal to 2, 8, 3, 27. Hence, the range of R is 8, 27. Show that the relation R in a set A is equal to 1, 2, 3, 4, 5 given by R is equal to AB such that modulus A minus B is even is an equivalence relation. According to the given condition, the absolute value of A minus B must be even. See the relation. AB such that modulus A minus B is even. For equivalence relation, we have to prove that R is reflexive, symmetry and also transitive. Let's check reflexive. Let A belongs to A, then modulus A minus A is equal to 0, which is even. That is, 0 is divisible by 2. Therefore, R is reflexive. Then symmetric. Let AB belongs to A, then modulus A minus B is even, which implies to minus of B minus A is even. That means modulus B minus A is even. AB belongs to R implies to BA belongs to R. Therefore, R is symmetric. Then transitive. Let A be C element A, then modulus A minus B is even and modulus B minus Z is even. Now, modulus A minus C. Add and subtract B, then we can see that modulus A minus C is the sum of two individual even numbers A minus B and B minus C, which implies to modulus A minus C is even. That is, AB belongs to R and BC belongs to R implies to AC belongs to R. Therefore, R is transitive. Hence, R is an equivalence relation. If R is a relation defined on the set of natural numbers n as follows. R is equal to xy such that x element n, y element n and 2x plus y is equal to 24. Then find the domain and range of the relation R. Also check whether R is an equivalent relation or not. See the condition given. 2x plus y is equal to 24. Now let us write this relation in roster form. We get the ordered pairs 1, 22, 2, 20, 3, 18, 4, 16, 5, 14, 6, 12, 7, 10, 8, 8, 9, 6, 10, 4 and 11, 2. We get the domain 1, 2, 3, 4 up to 11 and range 2, 4, 6, 8, 10, 12, 14, 16 18, 20 and 22. Now let us check whether R is equivalence or not. Reflexive. A belongs to the domain of R, but AA does not belong to R in the case of 1, 1, 2, 2, etc. Therefore, R is not reflexive. Symmetric. Here, AB element are, but BA not an element of R. That means 122 present in R, but 22.1 is not in R. Therefore, R is not symmetric. Transitive. There is no element such that AB element R, BC element R belongs to AC element R. Therefore, R is not transitive. Hence, R is not an equivalence relation. That's all for today. Practice well. We'll meet in the next class. Thank you.